All right, so thanks everybody for tuning in, and thanks everybody for the overwhelming support of this program. I'm really excited that it's going so well so far, despite not being in balmy Santa Barbara as I had originally planned when applying for this a couple of years ago. My tutorial is primarily, it's a little bit different than Mark's. It's kind of a tutorial on how to use a computational tool for better analyzing and understanding simulations that might be in different formats of the circumgalactic medium, anywhere from, when I'm talking about simulations, I'm primarily talking about volumetric hydrodynamic data sets. So this is either cosmological simulations or cosmological zoom simulations, or even idealized simulations of little chunks of the CGM or ISM or even IGM, really. So I'm going to do a really quick background on both the simulation side as well as the observation side, simply because I find that we all get kind of down in our corners of things and sometimes forget about how the other side is doing things. So, and since we're trying to make comparisons with simulations against observations, it's important for simulators to know what sort of things they're trying to compare against. So this is just a cartoon showing something that probably everyone here is familiar with, that traditionally, historical data of the CGM observationally was conducted by quasar or galaxy absorption line spectra studies, where you have a bright background source with a well-behaved spectrum, and the sight line that it takes traverses some sort of intervening material, perhaps close to a galaxy, and that produces absorption line features in the resulting spectrum. And the identification of the various absorption lines that you find tell you something about the ions that are present and the behavior of that gas along that column, that line of sight column. This was a plot that was showed yesterday by Xiao Wen. Really instructive plot from Jason Tumlinson, Molly Peoples, and Jess Works. Great review paper from a few years ago. So this is a phase diagram where the x-axis is density, the y-axis is temperature, and you can see various different ions populating this phase space of gas, with more energetic ions in the upper left probing, let's see, I can use my cursor, probing more high energy transitions that tend to reside in hotter, lower density gas, and then lower ionization ions in more dense and cool gas. And that tells you a lot about the state of the gas if you can identify which ions are present as your absorption lines. And furthermore, when you look at the actual data, so on the left, this is COS halos. On the right, it's the Keck baryonic structure survey. So on the left, when you identify individual ions that are present based on their position in the spectrum, or something to do with the doublet or a triplet, you not only identify the ion that's present, but you can figure out something about the width of it and the depth of it that tells you about the content of that, the content of the gas along that line of sight. And then you can take an ensemble of these and put them together into a radial profile, like is done on the right side, where the x-axis is projected distance from the galaxy or impact parameter, and the y-axis is like equivalent width of the absorption line or column density, or something about the strength of the amount of material in that particular ionization state. So now we know, like, nominally what we as simulators are trying to compare to in terms of doing analysis that directly applies to UV, optical, infrared absorption line data, but in some ways the code that I'm about to present can also work with other types of CGM data, simulated data. Oops. Okay, so the two codes that I'm presenting, Trident and YT, are both Python open source codes with a variety of different contributors. First, YT, you probably have heard of. It's a really general code that's used for visualization and analysis of really any volumetric data set. When it was first started to be developed by Matt Turk, who's now a professor at Illinois, it was primarily for astrophysical hydrodynamics data, like I'm showing here, but it has grown to a much, much larger community with scores of different contributors, and many of them are actually present on at this meeting. the Trident code is an extension of YT specifically for dealing with CGM and IGM hydrodynamic simulation data, and for generating synthetic observables. We definitely have a smaller contributor base. The main authors who developed it were myself, Britton Smith, and Devin Sylvia, although, as I said, there are a number of different developers, and again, many of them are here today. But again, these are all free. They're all freely available, have decent documentation, and you can download them and run them on Python on your own machine and on your own data. So the main functionality that Trident provides is that you can generate ion data for your simulations. Most people, when they run simulations, don't have the specific ionization states of different elements. When they're running the code, it gets quite expensive, although there are some exceptions. Ben has been involved in some of that work. But most of the time, you don't necessarily have ions beyond neutral hydrogen and ionized hydrogen present in the simulation at base level. And Trident uses some reasonable assumptions to generate that ion data for any arbitrary ion in your simulation data and kind of stack it on top. It also enables 1D analysis along skewers, much like you'd get from absorption line features to background quasars. And finally, it can generate, again, using some decent assumptions by depositing Voigt profiles in a broadband spectrum, it can generate absorption line spectra for making direct comparisons with observations. And then YT does a bunch of stuff, but primarily here I'm going to use it to visualize spatial distribution of gas and then correlate different gas fields in phase plots. Okay, so again, quick review. What is actually in a hydrodynamic simulation data set? Here I've represented it as a grid, but this could equally be a particle-based or a non-regular grid, like a repo and a moving mesh. It's essentially a volumetric data set where you have a number of different resolution elements, and each resolution element describes the behavior of a fluid element, some sort of gas component. And for each fluid element, there should be a variety of different fields. Sometimes it's something like density, as we can see here, or temperature, or metallicity, or the velocity of gas in the x direction, or so on and so forth. But as I said, and just simply from that, you can use YT and Trident to generate something like this. This is a movie from one of the fire data sets that I produced, and it's essentially just generating a single projection plot for each frame in a time series of outputs from the fire simulation. So you can use this for both analysis, but you can also use it to gain some sort of, I really like these to gain some sort of intuition about what's going on in the simulation itself. This is a Milky Way mass halo evolved from high redshift to low redshift and you can see density and temperature over time. Okay, but what we'd like to do is look at the individual behavior of ions. And as I said, this isn't by default included in most simulations as they're run. So Trident provides a module called ion balance, which consists of a lookup table that has almost 1 million different elements because it was run almost 1 million times on different cloudy simulations with different cloudy initial conditions of density, temperature, metallicity, and in this case, redshift, which tells you something about the UV background at that particular redshift. And so these get into an equilibrium state. The cloudy runs got into an equilibrium state for that density, temperature, and redshift. And then we pull out the relevant phases of the gas once it's kind of converged. And based on that, we can populate each cell or each resolution element in our simulation with additional fields for these ions. So I can put in neutral hydrogen, which, as you can see, has this is a kind of a sample data set that is a very low resolution data set for the purposes of this, but it's much more filamentary in the distribution of H1 as opposed to something like oxygen 6, which is much more broadly extended throughout the halo because it's probing warmer gas, lower density gas. Okay, and then from that, making a similar video showing, again, H1 on the left and oxygen 6 on the right, and kind of showing the evolution of these two different phases, which is more akin to something that we might be able to see with observers, as opposed to an abstract quantity like temperature. At the second half of this tutorial, I'm actually going to go through a Jupyter Notebook and take you through a lot of the steps in generating things like this. And I will be providing that Jupyter Notebook afterwards so people can use that in the future. Okay, the second, as I said, the second piece of functionality that Trident provides is what we call light rays, but it's essentially just skewers, one-dimensional skewers that you can probe whatever fields you care to probe along arbitrary sightlines in your simulation data. And it looks something like this. So again, a movie to demonstrate this, but every slide is an output from YT and Trident. We're looking at a simulation on the left side, the spatial two-dimensional slice through a galaxy simulation, and you can see as that sightline traverses that volume, as it encounters material, you can see a bump in the density on the top profile. I arbitrarily chose silicon-2 as the particular ion to look at, and then line of sight velocity of the gas as we're probing through this volume as well. So you can probe that sort of thing with any of the fields that you care to from the simulation data, but most obviously this is appropriate for specific ions. And then finally, Trident can generate some synthetic absorption line spectra from that data, where it deposits a Voigt profile for every fluid element that it traverses that has whatever ion we care about, in this case silicon-2. And so it identifies if it's redshifted or blue shifted according to the line of sight velocity of the gas containing it with respect to the observer, and then deposits various different Voigt profiles in the final spectrum that we get out. So that's kind of the basics of how this is run. I'm going to skip past this and go straight to the tutorial. So let's see if I can view share. Okay. Okay. So as I said, I'm going to take you guys through a Jupyter Notebook that kind of demonstrates how to use all of this in reality, not just me hand waving about how this is done. I will provide this after the fact, so people are welcome to download this and use it and test it out. There's also relevant documentation on the Trident doc site on Read the Docs, but this may be a little bit more helpful. So I'll step through this rather quickly just to give you guys a feel for what's going on. Initially, I'm going to load the YT and Trident modules. I'm also loading IPython display just so I can display images inline in this particular thing. I'm working with a low resolution FHIR data set that is freely available at this website for the YT. YT has a number of sample data sets that you can use to test out functionality on a variety of different data sets. So I define that as a file name. I load it using yt.load of that file name to provide a data set. And then I just look at what fields are present for that particular data set. And you can see those of you who are Gizmo or Gadget users or Arepo probably recognize many of these. But if you go down to the bottom, gas, each field is a tuple, and the ones that start with gas are usually the ones that are relevant for the gas fields and so on and so forth. So you can see things like there's a variety of different fields that are present. I'm just going to do the simple thing of finding the centroid of the simulation, or finding the maximum density location in the simulation with this find max, and then generating a projection plot in gas density centered on that kind of high density peak with a width of 1 megaparsec. And this is just modifying things a little bit to give some nice text and adding a scale bar. And then I'll show it. I've also included the save command if you wanted to save it as a PNG rather than displaying it in your Jupyter Notebook. So this is what our simulation data set looks like with a galaxy in the center, a large halo around it. This is in projected density over 1 megaparsec. We can similarly do that exact same thing where I just swap out the field that I want to make the projection plot of. This time I'm doing it with temperature, and I'll give it a weighting of density. and generate, and I'm doing this down the x-axis, but I could just as well be doing this along the y or the z-axis or some arbitrary vector that I specified later. So this is what the temperature looks like for that particular data set. Hot, and then there appears to be a satellite that's coming in that has substantial cool data associated with it, or cool gas associated with it. And so, oh shoot, what happened? Similarly, I can generate a phase plot like we saw before. This is of density on the x-axis, temperature on the y-axis. This is for the entire volume, but if I specify halo, which is the region directly around the galaxy itself, I get a more realistic looking phase plot with a cool gas component and a hotter gas component. Again, this is a low resolution sample data set, so it shouldn't be taken too seriously, but it's just for the demonstration purposes. Okay, so as I said, I want to add ion fields that may not be present in the original data set. I can do that using Trident.add ion fields, and I'm going to specify carbon, nitrogen, oxygen, magnesium, and silicon too. Although I could also just say silicon as a whole and get all of the silicon ion fields. And you can see here that now these are present. It's a weird, the fields have to be named in a weird way to make it work. So H_P0 refers to H+0, which refers to H neutral hydrogen, H1. And oxygen 6 is similarly oxygen_P5 for oxygen +5. But that's how you can find these things. And now that these fields are populated in our data set, we can make projection plots of those fields, just as we did for the density and for the temperature. Clunking along here. Okay, and so this is our H1. Again, not necessarily realistic because this is very low resolution data set, but you can see the idea. And similarly, we can do this for oxygen 6. Oxygen 6. Here we are. So it's much more extended in its distribution than H1 was. And because those fields exist, we can do any of YT's functionality on them. We can make phase plots as well. So in this case, it's the same plot that we saw above with temperature and density, but now the weighting is oxygen 6 mass. And you can see that kind of the peak at which oxygen 6 occurs is in fact at 3 × 10⁵ Kelvin, which is where we nominally expect it to be based on the population of that particular ion. Relative to other phases, ionization states of the oxygen gas. So we can create a light ray, which, as I said, was this one-dimensional skewer. In this case, I'm going to make the start be at the center of the galaxy and the end of the ray be at just the edge, the boundary of the simulation volume. And I use this make simple ray command to generate that. It's rather quick to generate a light ray. It takes a few seconds. It's barking at me because some of the ion fractions are unrealistic from our lookup table. And then I can overplot this light ray on a projection like we saw before, just to visualize what its path is. And here you see, as I said, it starts at the center of the galaxy and ends at the domain edge, which is beyond the region that we're projecting in this plot. But we can look at that particular light ray and see what's present there. Again, it consists of fields. It's just a series of one-dimensional arrays representing the state of the various different fields along that line of sight. It has, in this case, it has over 2,000 fluid elements for that light ray. And we can look at the path length of each of those fluid elements, which is DL. And it's some of them are rather long in kiloparsecs, some are rather short. It's mostly dependent on the density of particles at that region that the line of sight that the light ray is traversing. We can look at other fluid quantities on that light ray, like neutral hydrogen number density, that provide us with values. Again, sometimes there's no neutral hydrogen, sometimes there's a bunch of neutral hydrogen that's present. And thus we can calculate the column density of H1 along that light ray simply by multiplying the path length times the neutral hydrogen number density that gives us column densities for each of the fluid elements along that light ray. And if we sum them up, it gives us the total amount of H1 along that light ray, that skewer. In this case, looks like a DLA. And finally, let's generate a spectrum for that particular thing, that particular sight line. There's some pre-entered information to give us different costs, cosmic origin spectrograph settings. In this case, G130M as the setting, and I'm just going to generate a Lyman alpha spectrum according to the presence of H1. Now remember, our sight line took us right into the center of that galaxy, and so yes, there's a lot of H1 that's present, and this is what you might expect in terms of that Lyman alpha profile that comes out of it. We can look at the spectrum generation that we created just to see these are the various wavelength values in angstroms, and then it provides also the optical depth field as well as the flux field. Sorry, this is going quite so fast, but it's only 20 minutes or so, and I'm ending imminently. Finally, we can generate a user-defined spectrum that, let's just say, arbitrarily goes from 1,000 to 2,000 angstroms, and we'll include Lyman alpha, we'll include magnesium too, and we'll include carbon lines. Because we're going through this dense region in the galaxy, it takes a little bit more time to generate these. See, it's clunking through here. Here we go. Here's our output spectrum. Now this is a pure spectrum without any kind of noise that's been added to it, but we can also add a background Q as like quasar spectrum to it and add Gaussian noise consistent with a signal to noise of like 30. When we do that, it generates something that may be a little bit more realistic for comparing with observations. And finally, we can generate spectra in velocity space. This is doing so, I just arbitrarily chose the nitrogen 5 lines to plot, and it shows us that, for the nitrogen 5 lines, we have a couple of different features. One at a velocity offset of 0, and then one kind of blue shifted with respect to the observer. So I hope, I know I went through that rather quickly, but I hope, let's see, I hope you get a taste for what we're trying to do with Trident and with YT in terms of helping people to better understand what the heck is going on in simulation data and perhaps make some relevant comparisons with observational data, at least UV, optical, and infrared absorption line data. Thank you.